It's a staple of high school science classes across the country. Students build a small rocket, they set it up on a launch pad, and they let it fly. It's an engaging project, but it begs the question, what makes rockets work? They're the product of some of the greatest minds of the past century, a feat of engineering, science, and math. But really, if you want to know what makes that rocket fly, you need to look into chemistry.
Let's start with what's perhaps the most significant performance metric in all of rocketry, the specific impulse. The specific impulse describes the efficiency of the rocket. You can calculate it by dividing the total impulse by the weight of the rocket. You divide by weight instead of mass, since dividing by weight will give you a result in seconds, a nice easy unit to work with. A second equation also exists, where you divide by the velocity of exhaust over the acceleration due to gravity. The acceleration due to the gravity in Earth's case is 9.8 meters a second squared. You can do this since the thrust, that is the push of the rocket away from the Earth's surface, comes from the exhaust. Now, the higher the specific impulse, the higher the efficiency and the less propellant required. Every little bit of weight will decrease efficiency, increase the amount of propellant required, and can significantly alter the cost of the rocket. Dense propellants will require smaller tanks, which will reduce both the weight and the overall footprint of the rocket. As mentioned before, this reduction in weight can be extremely beneficial to both the cost and the efficiency of the rocket. Low-density propellants pose an additional engineering challenge as well. The less dense the propellant, the more fluid needs to be moved in comparison to a propellant of higher density, which means you will need a more powerful pump. However, propellants with low density are not entirely to be written off. Propellants with a high specific impulse, but a low density, can still be very useful in the first stages of a rocket, when the power matters much more than the exact weight efficiency. Propellant handling is also another important consideration when designing a rocket. Certain fuels can be toxic or even carcinogenic, while others can require extreme exotic cooling to keep them in the correct state. While others still, they may just be easily handled and safe to use. The ease of handling propellant can also limit the capacity that a given propellant might be used in, or affect the overall cooling design of the rocket. To learn more about rocketry, I contacted Adam Trumper from Launch Canada, who graciously agreed to help explain how rockets work.
So, everybody's tried the thing where you blow up a balloon and then you let it go, right? And it'll go fly around the room. That's at the most basic level how a rocket works. You definitely could not build a launch vehicle using a giant balloon with pressurized air. But it would be a rocket, and you could still calculate what specific impulse that would work out to. One step up from that is what they call a cold gas thruster.
Cold gas thrusters provide one of the simplest methods of rocketry. A valve is opened on a tank containing a cold gas held at a high pressure. This gas is often either helium or nitrogen. The escaped gas is directed out of a nozzle, generating thrust. These thrusters are often employed on devices which are already in space, like satellites. This is because when you're in microgravity, the low specific impulse and little thrust generated by a cold gas thruster can actually have a decent impact.
So if you heat that gas, you could put a heater in it, you could do something else. That's going to improve your specific impulse a little bit more. So a warm gas thruster will be a little bit better performance than a cold gas thruster.
As the name implies, warm gas thrusters are just like cold gas thrusters, but with hot gas. A heater in the tank warms the gas before it's released. Since particles at a higher temperature are more energetic, the energy released by a warm gas thruster is greater than that of a cold one. This increases both the specific impulse and generates more thrust for the thruster. While the simplicity of a gas thruster makes them easy to design and implement, their specific impulse is simply not that high. If you need a more powerful rocket, you need to turn to chemical reactions, monopropellants and bipropellants.
That's it. Whenever you've got a separate fuel and oxidizer that react together, that is a bipropellant, whereas if you just have a single chemical that decomposes with a catalyst or with something, that would be a monopropellant.
If given time, certain chemicals will decompose on their own. Some of these chemicals can be used as monopropellants. To speed up the decomposition reaction, a catalyst bed will often be installed inside the rocket. Pressure fed out of their tank, the monopropellant will flow over the catalyst bed, speeding up the reaction. This will create exhaust, which can be sent out a thrust chamber, out a nozzle, generating thrust. An example of a common monopropellant would be hydrazine. Both monolethylhydrazine, or MMH, and unsymmetrical dimethylhydrazine, or UDMH, can be employed in such a system. Contact with a metal catalyst, such as platinum or iridium, will cause hydrazine to decompose into ammonia, hydrogen, and nitrogen gases. And these gases are then exhausted to create thrust. Regrettably, hydrazine is actually extremely toxic to humans, carcinogenic even, rendering it very difficult to handle. Hydrogen peroxide is another common monopropellant. In high concentrations, it breaks down into hydrogen, oxygen, and water vapor with the aid of a metal catalyst to expedite the reaction. This makes up the exhaust, which can be used to power the rocket's thrust. Overall, monopropellants perform moderately well, generating far more thrust than gas thrusters. But when compared to bipropellant systems, they just don't stack up. If you need to further improve your rocket performance, a bipropellant rocket is the way to go. In a bipropellant system, two separate tanks are used, one for the fuel and one for the oxidizer. By means of controlled valves, the fuel and the oxidizer are then injected together. If these chemicals react upon contact and burn on their own, they are known as hypergolic. An example of a hypergolic bipropellant would be hydrazine as a fuel, reacted with nitrogen tetroxide as the oxidizer. However, some bipropellants are simply not hypergolic and will require some outside sort of ignition to begin burning. Bipropellants are by far the most powerful option for a rocket. Rockets are split into two different groups based on the physical state of its propellants. Solid rockets will make use of a solid fuel and solid oxidizer, and liquid rockets will make use of a liquid fuel and a liquid oxidizer. In a solid rocket, a solid fuel and solid oxidizer are mixed together, sometimes with a binder, then cast into a combustion chamber and burned. This generates thrust. This is a relatively simple method of propulsion. It dates all the way back to the invention of gunpowder, with gunpowder being a fuel composed of charcoal and sulfur, oxidized by potassium nitrate. The composition of the propellant in solid engines like these guys right here are quite similar to gunpowder, and it's quite effective at launching lightweight rockets like this one right here. However, gunpowder and solid propellants like these engines, they're insufficient to launch a modern day heavy rocket, so other fuels and oxidizers are often employed. NASA's space shuttle made use of a solid propellant, primarily consisting of aluminum as a fuel and ammonium perchlorate as its oxidizer, with a polymer acting as a binder. Liquid rockets, on the other hand, employ propellants in a liquid state. They are by far the most popular choice in high-performance rocketry. The propellants used in liquid rockets can have quite a lot of variance among them, and can be divided into two main categories: cryogenics and storables. Cryogenic, or cryo propellants, can be immensely powerful, but they have one major flaw. They have to be held at extremely low temperatures. They cannot be kept in a liquid state indefinitely, because you can only cool them down for so long. The cryogenic oxidizer is almost always liquid oxygen, or LOX for short, which needs to be kept at least negative 183 degrees Celsius at all times. Two of the most common fuels to be combined with LOX are a special rocket grade of kerosene known as RP1, which is actually a liquid at room temperature, and liquid hydrogen, or LH2. To learn more about the differences between these two fuels, I contacted Western University's Western Rocketry team, who graciously agreed to help me out.
So two common rocket propellant combinations are burning liquid oxygen and liquid hydrogen, and another one is kerosene, or a refined form of it, RP1, liquid oxygen. So the use of liquid hydrogen and liquid oxygen permits a much higher specific impulse, which is a measure of efficiency in rocketry. So liquid hydrogen and liquid oxygen provides a higher specific impulse than liquid hydrogen and RP1, or kerosene. So the trade-off you get between using hydrogen and liquid oxygen and kerosene and liquid oxygen is that liquid hydrogen is significantly less dense than liquid kerosene. So as a result, you need a significantly larger volume of tank to store all the liquid hydrogen you need for your rocket. So all this extra tankage costs extra weight. The weight of anything in a rocket is very important, as any additional weight added generally is going to take away some possible weight of the payload.
And it's much more expensive to work with.
Yes. With liquid oxygen and liquid hydrogen, you require, since it's much less dense, you need significantly more complex pumping systems to achieve the same thrust of liquid hydrogen and kerosene, which you don't need to be pumping as much fuel at the same time for an equal amount of thrust.
Due to their limitations, cryogenic propellants are commonly relegated to the earlier stages of a rocket while they can still be adequately cooled. NASA's famous Saturn V rocket, which launched astronauts all the way to the moon, made use of RP-1 in LOX in the first stage of the rocket in the F-1 engines, while the J-2 engines of the second and third stages used LH-2 in LOX. SpaceX's Falcon 9 uses RP-1 in LOX as propellant, while NASA's currently in development SLS rocket will use LH-2 in LOX. Cryogenics can be brilliant if well implemented, but if you need to hold the propellant for an extended period of time, turn to storables. The major advantage of storables is right in their name. They can be stored indefinitely. Additionally, they are hypergolic, meaning there is no need for external ignition. All that sounds great, right? Well, storables also have a major flaw. They're very often toxic. Furthermore, they have a lower specific impulse than the most popular cryogenic solutions. Despite this, they are often used as high-power boosters or thrusters, while cryogenics will take the duty of being the main launch engines of a rocket. The hydrogen and nitrogen tetroxide combination I mentioned earlier would be an example of storable propellant. Since specific impulse is directly correlated to exhaust velocity, it's important to get as much exhaust moving as fast as possible. Low density, uncontaminated reaction products are imperative to getting that exhaust velocity up, since you push far more exhaust out far faster, permitting for more thrust per kilogram of propellant. It's for this reason that RP-1 kerosene and LH-2 are both extremely popular fuels. RP-1 and LOX will produce only CO2 and H2O as products, that's carbon dioxide and water, while LH2 in LOX produces only H2O, water. These are two extremely efficient reactions. Now, while at first glance it may seem best to have the fuel and oxidizer in these rockets in perfectly balanced stoichiometric ratios, turns out that that isn't as it should be. Instead, it's actually best to run the rocket fuel-rich. There's a number of reasons for this, not least that the oxidizer is typically far more dense than the fuel. Running fuel-rich produces overall less dense products, which, as I mentioned earlier, can work wonders for the exhaust velocity and, by extension, the specific impulse. While the exact balance varies from case to case, a general rule of thumb is that the stoichiometric ratio of a rocket's propellants should lean towards being fuel-rich. So if you have a rocket with RP-1 in LOX, it should be RP-1 rich. With LH-2 in LOX, it should be LH-2 rich. Unless the propellants are hypergolic, you're going to need some way to ignite them. There's a couple of ways to go about this. Number 1. Much like a spark plug, rockets can employ a small motor or torch igniter to get the fuel ignited. Or number 2. LOX rockets can use a pyrophoric chemical to cause ignition. Pyrophoric chemicals ignite on contact with oxygen. In a rocket using LOX as the oxidizer, adding a pyrophoric will cause it to instantly ignite. A common pyrophoric igniter is triethylaluminum mixed with triethylborane, or TTAB for short. TTAB provides a reliable ignition for rockets like SpaceX's Falcon 9 rocket. You see the green flash in this video? That is the telltale sign of TTAB ignition. And lastly, always ignite rockets from a distance. Hot gas plus high velocities does not mix well for the human body. Pressure is the name of the game when it comes to handling liquids in a rocket. Turbopumps will move fluids between tanks and chambers at high pressure. They are often centrifugal pumps, relying on rotational kinetic energy to generate movement. Rocket turbopumps are specifically designed to deliver even extremely cold cryogenic liquids with the correct flow rate and at the correct pressure required for injection. Without a turbopump, liquid rockets would be unable to move the propellants in other various chemicals, and would thus be unable to start any of the all-important chemical reactions. Rockets get hot. They get very hot. And since we don't want the rocket to melt its own engine away, we need to cool that puppy down somehow. One method of cooling rockets is known as regenerative cooling. Regenerative cooling is, well, cool. It's done by lining the inside of the rocket with small passages. Then, a propellant, normally the fuel, flows through these passages before being burned off for exhaust. Regenerative cooling is quite resourceful, since it only requires what liquids were already on board. Its main caveat, therefore, is that it requires the propellant to be a good coolant. This is not always the case. Alcohol works excellently as a coolant. Kerosene? Not so much. Kerosene will actually leave deposits of carbon, known as coking, up in the passages. RP-1, the rocket grade of kerosene I mentioned earlier, it's been tuned to reduce this coking and improve the cooling capabilities, although it's not perfect. Hydrogen, LH2, is also a common coolant in such a system. Ablative cooling is another method of preventing overheating in a rocket. The material which lines the walls of the rocket will be sacrificed in an ablative cooling system, burning up in the heat. This chemical reaction of burning will dissipate some of the oppressive heat in the rocket, radiating the thermal energy away, cooling it down. Whether they be solid, liquid, or a hybrid of the two, rockets are being constructed all the time by a passionate community of inspired individuals. From lone wolves to local clubs to university teams, there exists a grassroots rocket engineering scene, as long as you know where to look. Amateur rocketry competitions present a great challenge for aspiring students or dedicated enthusiasts alike to practice their skills and learn the ins and outs of rockets through practical experience. Launch Canada presents one such contest. University-level students from across the country can compete in a positive environment while developing the Canadian rocketry scene. There are plenty of competitions like this, and if you're a university-age student who's inspired to go out and create rockets, I recommend that you go and find one of these competitions and join a team. Hailing from London, Ontario, Western University's Western Rocketry team builds rockets to compete in a variety of competitions, including those put on by Launch Canada. Currently, they employ solid rockets based on ammonium perchlorate. This bipropellant includes an integrated oxidizer, and it provides them with a great base to design the rest of their solid rocket. The propellant is relatively safe and fairly easy to procure, even given existing chemical restrictions and regulations. The bright students hope to expand into other types of rocketry in the future.
You don't have to be a rocket scientist to build rockets. There exists a thriving community of amateur rocketry enthusiasts who would be happy to accept you. Building your own rocket from scratch or from a kit can be a great way to get involved, and you can check in your local area to see if there are any rocketry clubs. If you're a student, organizations like Launch Canada run competitions for teams like We Rocketry, which allows you to compete in a constructive environment. Now, let's go launch some rockets. And that's the chemistry of rockets.